Okay. Good morning. So let me know if you can't hear me, or if you can hear me. Good. I'm glad you enjoy the comics. That's I have fun searching for physics comics that match the topic of the day. This one doesn't quite match the topic because this one is about friction, but though we are going to talk about friction today, so because now that we know what friction is, we can include it in our problems. So we are moving on to chapter 6, and we are moving on to start looking beyond forces and kinematics and start looking at things like work and energy. So now I'm going to switch over to my PowerPoint here. Okay, let's see if this works. Okay. So there's our comic again, which hopefully you've all seen. It's sort of just illustrating what would happen if friction went away, and for that matter, if air went away, which would be a bad thing. Because if friction went away, you could no longer move around. You wouldn't be able to push off the floor, for example. At least and not go sideways. So before I talk about physics, I just wanted to talk a little bit about the first test. So I am going to post the test one long problem marks and send back the work this afternoon. Ali was the TA who did all that marking, did all that hard work. The marks look pretty good. So if you do have questions about how your long problem was marked, you should talk to Ali. Okay, he's your first point of contact for that, and then he'll talk to me if there's any issues that go beyond him. All right, so he's the person you need to talk to. And then just a reminder of what I said in the announcement over the weekend, that I'll give you half marks back, just this one time, half mark back on a long problem numerical answers in Canvas if you got them correct in your CrowdMark submission, but they're not right in your Canvas quiz. And if you want to get these marks back, you have to send me a message using Canvas email with the subject test 1 mark adjustment, okay? With your full name and your student number and which parts of the long problem you want me to look at. And then if you had a documented computer connectivity issue, some people already sent me screenshots and things, or I know that you were having problems with your camera or something, or there was a rounding error. There was a square in the answer, and so in a few cases, rounding messed things up. Then again, send me an email and remind me about it, please, because I want to collect these all in one place, and I will do them all at the same time. And I will give you full marks back if those were your issues. Okay? So, and let me know which issue it was. So, and that way, I'm going to wait till these all come in, and I'll probably do all the mark fixing over the reading break, which is in a week from now, which will be nice. So yeah, so the numerical answers that you submitted were included in the initial auto-graded result. Yes. Yes, I'm going to make the multiple choice visible this afternoon too, so you can have a look at that. Other questions about this? Okay, I don't see any more questions, but if you do have more questions, feel free to ask me via Canvas email or put them in Piazza so everybody can see the answer. Okay, and like I said, I'm not gonna do it immediately. I will, once I've collected them all over the next week, then I will do them all in one batch. That's just more straightforward for me. Yes, it's only 3 out of 4 tests that get counted for your final grade. All right, so now I think we're going to move on and talk about some physics. So like I said, we are moving on to a new topic. We're going to look at what's called work, which is a very generic sounding word that we use in everyday language that has a very specific meaning in physics. So you have to be a little careful when you talk about work. So basically there are 2 ways to look at what happens to an object when a force acts on that object over a distance. one way to look at it is what we've done already, which is to use Newton's second law. We know that the net force on an object produces an acceleration, which changes the velocity of the object. And we can use our kinematic equations to examine the motion and look at what's going on. So use Newton's second law and then kinematics, and you can figure out the motion. So that's one way to do things. The way we're going to learn about today is what I call the work-energy theorem method, okay, which is instead of looking at in terms of force causing an acceleration, we're going to say the net force does work on an object, which results in a change in kinetic energy of the object. So let's go through and talk about what's work and what is kinetic energy, which is essentially the energy of motion. Okay, so say for example, you are running through the airport and you're dragging your roller bag with a force F at an angle theta above the horizontal, and your roller bag undergoes a displacement d. So one thing to notice when we talk about work is we're going to use little d for the displacement. So remember, that's just the change in position for the object. For most cases, it'll be a one-dimensional change in position. So I decided to go with d because both the book and the pre-lecture videos are using little d as a vector here. So just be careful, this is not a distance, this is the displacement of the object, which is different, right? So if you know the displacement and you know the force and you know the angle of the force, then you can calculate the work, because the work, in this case, the work done by the force F here is just equal to the magnitude of the force, the magnitude of displacement, and the cosine of the angle between the two. All right, so in this case, it's F times D times the cosine of theta. So what are our units here? Well, you can see what our units are here, right? Okay, force has units of newtons, displacement has units of meters, and if you take a newton times a meter, you get a unit called the joule, which we'll use capital J for. Joule is named after a scientist from the 1800s who invented a lot of steam engines, among other things. So, and as we'll see, the joule is also the unit for energy. So it kind of makes sense that he has this unit named after him. So that's what work looks like. So work is magnitude of force, magnitude displacement, cosine of the angle between the displacement vector and the force vector. That's where theta falls, between D and F. So if that's true, I'm going to give you a question to try. So let me start up the poll. Yeah. Okay, so the question is, you've got three forces and displacements drawn in the little picture, and the question is, which force does the largest amount of work? Assume all of the displacements are the same. So our displacement, little d vector, is that blue vector pointing to the right. Assume it's the same direction, same magnitude in each case, but what's different in each case is the magnitude and the direction of the force being applied. So the question is, which of those forces does the most work? And remember that work is magnitude of the force times magnitude of the displacement, which would be the same for all of these guys, times the cosine of the angle between the force vector and the displacement vector. All right, I think we'll do about 10 more seconds on this one. So if you're not sure, go ahead and guess. Okay, 5, 4, 3, 2, 1. All right, so let's see what the responses are. So what have we got? Looks like very much the vast majority, well, at least a very large fraction of the total group think that the answer is C, that the 6 Newton force does the largest amount of work. So let's have a look at this one and see what it looks like. So let's go through and calculate the work in each case. So if we start with the first case, okay, the one on the left, what do we get for work? Well, the magnitude is 10 newtons. The magnitude displacement vector is just D, cosine of 90. And then we remember that the cosine of 90 degrees is 0. So that force, perpendicular to the displacement, does 0 work. Then we look at the next one, and we have a magnitude of 8 newtons, displacement of D, and now we have the cosine of 60 degrees, the angle between the two vectors, and the cosine of 60 degrees is a half, and so we get 4 times D. Okay. And then in the third case, we have a magnitude of 6 newtons, D, and we have the cosine of 0 degrees, and the cosine of 0 degrees, we remember, is 1. And so this one is just equal to 6 times D, 6 newtons times D. And then if you were to plug in D in meters, you would get an answer in joules. So in fact, well done. Sorry, let me move the poll out of the way. Well done. Sorry about that. Then the answer is, in fact, 6 newtons. Okay, so the largest group was correct. Well done. That it is the 6 Newton force that does the most. Something can be moving, so it could have been moving before, and then there is a force, right, acting on it, right? You don't need force to have a displacement. Okay, so this is something moving sideways, and there happens to be a perpendicular force to it, and we're saying, does that perpendicular force do any work? And the answer is no. Okay, so that's a nice quick example of how to determine relative work between different situations. All right, so let's talk a little bit about the signs of work, because work is a quantity that can be positive or negative or 0, as we've seen. Okay, and the way you figure out the sign of the work done by a force F is by looking at the cosine part of that equation. Okay, the F and the D are all positive quantities, right? Are both positive quantities. Those are magnitudes of vectors, right? So the sign comes from the cosine, right? And if we look at our cosine function here, we can see that between 0 and 90 degrees, it's positive, but between 90 and 180 degrees, it goes negative. So we will specifically not be going beyond 180 degrees because we're talking about the angle between two vectors, okay? And it starts at 0, and then it goes to 180. And if we go past 180, we can just flip it over and use the angle that's less than 180. Okay, so we're always going to be choosing the smaller of the two angles. Okay, and so our thetas will run from 0 to 180, which means that it'll run from a cosine of 1 to a cosine of -1. So what does this mean? So when theta is between 0 and 90 degrees, then your force is doing positive work. All right, so if your force has a component in the direction of the displacement, you will get positive work. If theta equals 90 degrees, like that first scenario we had, okay, then the force does not have a component in the direction of the displacement. It's perfectly perpendicular, then the work will be 0. And then the last possible scenario is what if theta is bigger than 90 but less than 180? Okay, now the force's component along the displacement direction is actually opposite the displacement. So if like displacement was along the x-axis, the x component of the force would be negative, then the force does negative work. So that's the thing to keep in mind, is if a force is pointing opposite the displacement, has a component opposite the displacement, then it will do negative work. Okay, so any forces that oppose the displacement, okay, in any degree do negative work, and any forces that are in the same direction as displacement will do positive work. Okay. So that makes sense, right? Yeah, so you're only going to get increases in kinetic energy here, right, if your force points in the direction of the displacement. Okay, because then you'll get an acceleration in that direction. But if the force points opposite, you'll have an acceleration in the opposite direction, and that'll cause your object to slow down, right? Or speed up in that direction. Well, no, slow down. So, because we're talking about displacement in the positive direction. All right, so poll question number 2. This is similar to one that you saw in the pre-lecture. So I'm going to do this one fast because I think it's very, since it's so similar to the one you saw in the pre-lecture and the bridge questions. I can't remember which one it was. Okay, and the question is, so you have a ball tied to a string which is being whirled around in the circle. What can you say about the work done by the tension force on the ball? Okay, and the important thing to see here is that the tension is perpendicular to the velocity. Okay, and it remains perpendicular to the velocity for the entire circular path of the ball. Okay, and in this case, we're just looking at while it's going in a circle. We're not looking at what happened to get it going, okay, just while it's going in a circle. Okay, well, the displacement's tricky here, okay? So, it's the same for the entire circle or part of the circle. The answer will be the same, but think it probably most useful to think about small displacements and what those look like. If you're going to do larger displacements, then you have to look at the average tension over that. But I think the easiest thing here is to think about small displacements as you go around the circle. All right, I think we're going to do about 5 more seconds here. So if you're not sure, go ahead and guess. So 5, 4, 3, 2, 1. All right, so let's have a look at what everybody thought. And again, we've got lots of agreement. Everybody's in agreement today. So even more agreement this time. So we've got 147 people think that the answer is A. And in fact, that's the correct angle, sorry, the correct answer, because if the angle between the tension and the velocity is 90 degrees, then that means that the angle between the tension and the displacement, like I said, if you think about tiny little displacements as your ball moves around in the circle, your tension is always going to be perpendicular to your displacement, and so the tension will do no work at all. Okay, it's much like that other situation we saw where the force was up and the displacement was sideways. Okay, forces that are perpendicular to displacements will never do work on the object. And we're going to see that over and over again. One place we're going to see that a lot is an object on a flat surface and the normal force acting. We're going to see that that normal force is not going to do any work either. Okay, so now let's move on to our work energy theorem. So, okay, Nadia, you had a question? Is it a quick question? You need to type your question, or no? Okay, no, she's good. All right. So what's our work energy theorem? So the work energy theorem says that the net work done on an object is equal to the change in kinetic energy. And we're going to use K for kinetic energy. So whenever you talk about change, that means it's the final minus the initial. So in this case, it's Kf minus Ki. And how do we calculate kinetic energy? Well, it's equal to 1/2 the mass of the object times the magnitude of the velocity squared, which you could also call it the speed squared. Okay, so in this case, it's 1/2 mv final squared minus 1/2 mv initial squared. So for example, if we look at our roller bag as we're running through the airport, which hopefully someday we all get to go to the airport again, you can imagine that it has an initial velocity, vi, and it has some time later. This force has a component in the direction of displacement, so it's going to cause an acceleration. So you expect that if that's the net force, okay, it does depend on the net force here, okay, but let's say the net force is in the positive direction, does positive work, then you're going to end up with a larger final velocity, v final there, okay, and the idea is then you just take the mass times the magnitude of that velocity squared, and that gives you what's called the kinetic energy, which is the energy of motion. When an object is moving, it has a certain amount of kinetic energy. The faster it's moving, the more kinetic energy it has. And if you want to give an object kinetic energy, you got to do work on it some way. All right, so let's talk about network. So what exactly do we mean by network? Because this is probably one of the things that trips people up the most, is correctly calculating network in one of these problems. So it's the work done by the net force. So there are two choices to figure out how to do network, to figure out how big it is. You could determine the work done by each force that acts on the object. Okay, so it means figuring out what are the forces that act on the object, calculate the work for each individual force, and then add them up. That's one way to do it. The other way to do it is to find the net force. So look at all the forces as vectors, add them all up, find the net force, and then find the work done by that net force. They should give you the same answer if you did it correctly, okay, because they're equal to the same quantity. So it's your choice which way you do it. If you have time, like for a homework problem, sometimes it's useful to do it both ways, and that way you can check your work and make sure that you've taken all of the forces into account. And I'm going to hopefully have time at the end. I'll show you an example and we'll compare so you can see how that works. Okay, so another poll question. So this one, I think we're going to try and do this one relatively quickly. So let me just start up the poll. Okay, so here comes the poll. All right, so the question is, a car drives up a hill at a constant speed. What are the change in kinetic energy and the net work done on the car after it has traveled some distance up the hill? And the whole time it's traveling, it's moving at a constant speed. Okay, remember, net work is the work done by the net force. And you want to think about if something is moving at a constant speed, what does that tell you about the net force? Okay, I think we'll do about 10 more seconds. All right, 5, 4, 3, 2, 1. Let's see what everybody thought. So a bit less agreement now on this one. The largest group is going for C, that the change in kinetic energy is 0 and the net work is 0, that they're both 0. The next largest group is going for A, which is that the change in kinetic energy is 0, but the net work is greater than 0. And then we also have some votes for the opposite, that the change in kinetic energy is greater than 0, but the net work is 0. All right, so what is the answer here? And the answer is that C is the right answer. Basically, that's what the work kinetic energy theorem says. All right, that that the net work is equal to the change in kinetic energy. For an object moving at a constant speed, its kinetic energy isn't changing, right? Kinetic energy is 1/2 mass times velocity squared, right? V squared. So if its speed isn't changing, then its kinetic energy is not changing. And then if its kinetic energy is not changing, then the net work must be 0. Okay, I mean, there are forces acting here, right? There's a normal force, there's a weight, there must be some kind of friction, there must be some kind of drive force, right? But if there's constant speed, then that tells you the net force must be 0. And if the net force is 0, the net work is 0, and the change in kinetic energy will be 0. Okay, so it's always, always true. This is one of these fundamental laws. Sure, it can. Yeah, you have to be a little bit careful here about whether kinetic changes to gravitational potential. We're going to talk about gravitational potential energy next time. So let's leave gravitational potential energy out of the picture for now and just think about the work energy theorem. Okay, so it's true that your gravitational potential energy is changing here, but that doesn't automatically mean that the change in gravitational is equal to the change in kinetic energy. That's only true if you're a falling object and the only thing acting is gravity. That's not true here, right? There's clearly a drive force of some kind, right? Because if there wasn't a drive force pushing that, you know, if those wheels of that car weren't pushing on the ground, right, and then it would roll down the hill, right? It wouldn't go up the hill. So there's clearly another force going on here. All right, another poll question. This is similar to something we've seen before, but slightly different. So you should read it carefully. Well, we've only got 3 choices here. Okay, so what do we have? We have two blocks of mass M1 and M2, where M1 is bigger than M2. So you can see it's a bigger block there. And they slide on a frictionless floor and have the same kinetic energy. So they have the same kinetic energy when they hit a long, rough stretch that has a mu k, a coefficient of kinetic friction greater than 0, which slows them down to a stop. Which one goes farther before stopping? Okay, M1, M2, or they go the same distance. All right, and the key thing here is that they have the same kinetic energy, which means that since their masses are different, their velocities are different. Okay? So think about this in terms of the work done by the friction that's causing the objects to slow down. So friction's going to do work on our masses as they slide across the rough part. Okay? It's going to do negative work, and that's going to cause a negative change in kinetic energy, which causes the objects to slow down. You can't see the question. Can everybody else see the question? Okay, I'm not sure why you can't see it, Nandini. Yeah, make sure you're using Chrome too, if you can. Chrome is the best option. All right, I think we'll do about 10 more seconds here. So if you're not sure, go ahead and guess. Okay, 5, 4, 3, 2, 1. Let's have a look. So a bit more disagreement here, but so we still have the largest group are going for B, that the smaller mass, M2 is going to go further before stopping. And then the next largest group think that they go the same distance, but then we also have a reasonable group that think that the bigger one is going to go further before stopping. So let's have a look at how this one works. Let me end the poll. All right. So what's going on? So like I said, remember, it's the same kinetic energy for these two objects. Okay, so if they have the same kinetic energy when they hit the rough spot, then they must both have the same change in kinetic energy, which means that they both must have the same work done on them by the net force acting on them. Okay, because the net force, sorry, the work done by the net force equals change in kinetic energy. So if they're both undergoing the same change in kinetic energy, it means the same work by the net force, the same net work. In this case, when they're sliding on that rough part, the only force that does work on the blocks is our kinetic friction, right? The normal force up and the weight down are not doing work because they're perpendicular to the displacement. And we know that the net work done by the friction is minus the magnitude of the friction, Fk, times the displacement, d. Okay, and we get that minus sign because they're opposite directions, the friction force and the displacement. Okay, and then we think about, okay, how big is friction? And we know that the magnitude of the friction force is smaller or lower for M2, okay, because the friction force is proportional to the normal force, which is proportional to the mass times the acceleration due to gravity. Okay, so it's proportional to the mass. Okay, so if the friction force is smaller on M2, then the stopping distance must be greater for the two works to be the same size. Okay, and we need the works to be the same size because the change in kinetic energy is the same for the two blocks. Okay, questions on that one? It's again just applying your work kinetic energy theorem. All right, so I thought what we would do is for the rest of the class, we would work our way through an example. So yeah, so the answer was B there. Sorry, I forgot to choose it. Okay, so the smaller mass goes the longer distance. Okay, so the last point again is, so the works are the same. So that means that the magnitude of the force times the magnitude of displacement must be the same for the two different blocks. We know that the magnitude of the force is smaller, the friction force is smaller on M2, so the displacement must be larger for M2. So that means M2 is going to go a larger distance before it stops. Its displacement is longer. All right, so we're going to do an example problem. All right, and here we have another inclined plane problem. Okay, so this one says, so we have a block with a mass of 5 kilograms, and it's moving up an inclined plane that is 12.5 meters long. And the block starts with an initial velocity, VI, of 17.8 meters per second. It's going pretty fast. And the inclined plane is at an angle of 35 degrees from the horizontal, as shown. And we have friction. The coefficient of kinetic friction between the block and the incline is 0.25. What is the speed of the block at the top of the incline? Okay, so that's what we're going to try and figure out. And we've got our work kinetic energy theorem. You could do this with kinematics, but we're going to do it with the work kinetic energy theorem. So the net work equals the change in kinetic energy here. So to figure out the speed at the top, we're going to figure out the net work. So first thing, just like with Newton's laws problems, you need to draw a free body diagram of your forces, right? Because if you're going to figure out net work, you need to know the net force, or at least you need to know all the forces acting on our block. So if we look at our block, right, what forces are acting? Well, we know we have a normal force perpendicular to the plane. We know we have the weight, which is always vertically downwards. And in this case, because the block is moving up the plane, we have a kinetic friction pointing down the plane. And I chose to have my XY coordinate system so that positive X is up the plane, the direction of motion, okay, and therefore my Y direction is perpendicular to the plane along the direction of the normal force. All right, which is pretty standard for when we're doing slopes and inclined planes and things. All right, and now our displacement vector points up the slope. Right, so there's my displacement vector D pointing up the slope from the beginning to the end. Okay, don't worry too much at this point about exactly, we're typically going to talk about either measuring a block from the middle of the block or the beginning of the block. It doesn't matter too much. Okay, we're treating our objects like point particles right now. You can draw your vectors on the object itself if you want to. That's fine, Emily. I tend to draw it separately just so I can see what's going on because I wanted to put in that displacement vector and sort of separate things a little bit so I can see better. But it's fine to draw it on the block itself if you want. Okay, so let's start with the work done by the normal force. So this is the easy one because the normal force is perpendicular to the displacement. So when you calculate it, it's magnitude of the force, magnitude of displacement, and times d times the cosine of 90. So here's an example where the normal force does no work. Okay, it's not always true that the normal force does not work, but if you're sliding along a surface, okay, in that case, the normal force of the surface on the object will do no work because it will be perpendicular to the surface. So next one, work done by friction. So we're working our way around our forces. Okay, so what's the work done by friction, right? So it's the magnitude of the friction times the magnitude of the displacement, d, times the cosine of the angle between the friction and the displacement. And the angle between those two is 180 degrees because the displacement is one way and the friction is the opposite direction. So there's that minus sign that I wrote down in the last clicker problem, the last pole problem, right? So the work done by friction is minus the magnitude of the friction force times the magnitude of displacement. Okay. So now I'm going to plug in some numbers. So now I'm going to skip a step or two here because I know something about inclined planes because I've done inclined plane problems before, and I know that the magnitude of the kinetic friction is the coefficient of kinetic friction, μk, times the magnitude of the normal force. And we know when you're inclined plane, the normal force has a magnitude of mg cos theta, provided there are no other forces acting along that y direction. If the only two forces along y are the normal force along y and the weight, which has a component in the negative y direction of mg cos theta, right? So that's our normal force. That's the magnitude of our normal force is mg cos theta. And then don't forget to multiply by the magnitude of the displacement, d. So now we're going to plug in our numbers. So we've got 0.25 for our coefficient of kinetic friction, 5 for our mass, 9.81 for g, cosine of 35. Okay, that's the angle of the inclined plane here. Okay, and then our displacement is 12.5 meters. Okay, because we're trying to figure out how fast it's moving at the top of the plane. So we want the displacement for the whole length of the plane. And so what do we get? We get about minus 125.6 joules. So, and it's always useful to stop and think, okay, it's hard to know if the magnitude's right for that number, the size, but we know that the work has to be negative, right? We know that friction would be negative here, would do negative work here, right? Because the friction force opposes the displacement. Okay, friction is doing negative work on the object. Friction is causing the object to slow down. We are using the 35. Okay, so you do have to be careful with your angles. Okay, so the first angle, right, is the angle between the frictional force and the displacement. That's why that one's 180. And then the cos theta, mg cos theta, that is the magnitude of the normal force. Okay, so I just plugged in mu k mg cos theta for fk. Right? Because we've seen that a couple times now, all right, that the that magnitude of the normal force when you're on an inclined plane is mg cos theta. All right. So that's where we're at right now. So we have a negative work by friction, 0 work by the normal force. So here we are. It's going to flip over to the next page to give us some more room. All right. So we've got one more force to figure out the work for, and that's gravity. All right, so in the pre-lecture, they said one way to figure out the work done by gravity, okay, is you take minus mg times the change in the vertical position. Okay, so it's the final vertical position minus the initial vertical position. Okay, so in our case, if you look at what the block is doing, it's starting, let's assume that at the bottom of the plane, y equals 0. Okay, so we're starting with y initial equals 0, and we're ending up at the top of the plane, and the y value at the top of the plane is d sine theta, where d is the hypotenuse of the triangle, and theta is our 35 degrees. Okay, so d sine theta gives you the vertical leg of your right triangle. That is equal to your final y position. Does everybody get that? See where that comes from? Okay. So now, if we're happy with that, We can plug in our numbers. All right. So again, our mass was 5 kilograms, g is 9.81, our displacement is 12.5 meters, that's the magnitude of it, and then it's the sine of our 35 degrees, and we get, again, a negative work. So gravity is doing negative work here as the block slides up the plane, and we think about it, that makes sense, because the force due to gravity has a component opposite the displacement. Right? If we look at our forces here, we can see that the weight, which points straight down, right, is at an angle larger than 90 degrees from the direction of the plus x-axis. Okay? All right. So there is another way to do work by gravity. Okay, you can use your formula the pre-lecture gave you, that it's minus mg, the difference in the vertical position, y final minus y initial. Okay. Or you can just use our regular formula, which says R is equal to force, magnitude displacement, cosine of the angle between the two forces. If you do that for the displacement in the plus x direction and the weight, okay, and you look at the fact that the angle between the plus x direction and the weight is 90 degrees plus theta, right? Theta is our 35 degrees, then we could write it as mg, the magnitude of the weight, d, the magnitude of displacement, cosine of the angle between the weight and the displacement, which is the cosine of 90 plus theta. Okay, so that's just using our regular work formula rather than the one that the pre-lecture derived. That, and then you remember your trigonometry, cosine of 90 degrees plus theta is equal to minus the sine of theta here. Okay, and so you get that the work done by gravity is minus mg d sine theta. You get exactly the same thing as you had before. Okay, for the work done by gravity. In either case, and it should be the same, no matter which way you do it, you should get minus mg d sine theta. Okay, so that's good to know that things are consistent and you can do it either way. All right, and again, we can see that work does negative, gravity does negative work, okay, because it opposes the motion, right? The gravity wants the object to fall down. It's not causing it to accelerate up the plane. Yes, you could find the x and y components. That would be fine, right? That's essentially what's happening here, right? Is we're looking at the, essentially what's going on here is g sine theta is the minus g sine theta times m is the x component of the weight. So yes, you can also do it that way. That's totally fine. That's another way to do it. Okay, so now network. So what's a network? We just add up our works. First one was 0, so I didn't include it here. And then we have our minus 25.6 joules and our minus 125.6 and minus 351.7 joules. And we get minus 477.3 joules. Okay, so we've got negative work, net work, which means that the change in kinetic energy will be negative. So now we're going to do our work energy theorem. And we're going to plug in the net work, and we're going to plug in the initial velocity here and solve for what the final velocity must be. Okay, so what do we have? We have our net work there. We have 1/2 the mass of 5 kilograms, v final squared minus our v initial, which is our 17.8 meters per second. We square it. So if you solve that for v final, you get 11.2 meters per second. Okay, and it's the positive answer that makes sense, not the negative answer here, right? Because we're talking about something moving in the positive direction. Okay, so if the object were to turn around and go back the other way, the direction of the friction flips and things get more complicated. Okay, so in this scenario, if it's got a non-zero velocity at the top of the plane and it's going in the positive x direction with 11.2 meters per second. Okay, so does that make sense to everybody? Okay, it looks like you're answering each other's questions, which is good. But yeah, that's weight. That little, I wrote weight because the pre-lecture likes to write weight, but you're totally fine to write mg for your weight, just to clarify for yourself. And in fact, when we start talking about work, because work is W, it might be good not to use weight, just so you don't have too many W's rolling around. All right, we have run out of time after all of that. So I was going to show you another way to solve this problem. Okay, so yeah, work net is negative, so the object slows down. That's exactly what we expected. So since we ran out of time, what I'm going to do is I'm just going to post the other solution and let you have a look at it. But this is just showing you that you could work out the net force and then use the net force to get the work, and you would get the same answer. Okay, so I'm going to let you guys look at that over the weekend, and then you can ask me questions about that next time. Okay, so we're done for the day. Sorry I went over. I'm going to stop it recording.